Waalaikumsalam. Very good morning. Chromatography based student. Right, organic analytes using chromatography methods. Is then
Doktor, sekat-sekat.
so application of analytes. Okay, this is yes. Sekat.
Sekat-sekat. We cannot hear you well.
It's okay. Cannot hear me well. Cannot hear me. Right, wait for a. Can you hear me clearly or not?
Yes, Doctor.
All right. So, the purpose is for the first one is for micro and semi-macro analysis, and for removal of impurities from the sample and to concentrate the analytes in the sample. We only need to analyze the analytes in, right? So we need to let's extraction. We have sample and liquid sample, and liquid continuous. Right, for the liquid sample, right? So now we have liquid or the cross current, liquid current. Batch and continue. Now, more about the liquid to understand the equilibrium. Okay, mean by the equilibrium. Okay, dynamic equilibrium occurs when two reversible processes occur at the same rate. Many processes, such as some chemical reaction, are reversible, and when at dynamic equilibrium, the forward reaction will occur at the same rate as the reverse rate. So that we need to understand that for this liquid extraction to occur, we need to ensure that the equilibrium is dynamic, right? Meaning that the rate is at the distribution or distribution coefficient rate is KD, all right? Why my is not moving? Okay, so Kd is equal to concentration of our organic both are in reversible dynamic equilibrium, right? So liquid-liquid extraction, LLE, is also known as section and partitioning, right? How we do it, we just mix the solvent with the sample so that our solvent can extract out the analyte from the sample. And then we, at the end of the process, we assume that all the analytes have been extracted to the solvent, and we remove out the sample. That we assume that in the sample there are no more analyte inside the sample. So I will show to you after this how the is being done. So this method is done to separate compounds based on their solution preference for two different immiscible liquids, usually water and organic solvent. For this LLE, we need to make sure that will not mix together. For example, solvent and water, they will not mix together. All right. It is an extraction of a substance from one liquid phase into another. All right. So this example, we the separating funnel for the liquid extraction. Have you seen this funnel before this? The separating funnel. Normally, in the separating funnel, we have we have the close a valve, right? To inside, and then we have a funnel tab, all right? To at the end, for example, at the end of the separating process, we need to remove. For example, this is the sample that from the water, and then we have mixed with the solvent, okay, and we have shake and we have shake it well and solvent, right? And we want to remove the matrix, right? So this is how we open the funnel tab. All right. So for example, separation funnel, and then we put 10 minutes calorimeter organic solvent. All right, and shake for 2 minutes. Okay, raise the pressure while shaking, because after we shake the separating funnel, there will be some air pressure inside. So we make it upside down. Okay, we put this at the top, and then we open the funnel tab to remove the gas pressure. All right. And then we have a two layer. After we shake at the process, okay, we assume that all the analyte have been transferred into the solvent. So we have a two layer of solution. The first one is the aqueous solution, and then we have an organic solvent, right? And then okay, concentrate our analyte, and then we further the process for the consequence analysis. Right? What is this? What is the advantage of this method? It is simple, robust, and minimal operating training. Because we need to have the separating funnel, shake it, all right, and then we pre-concentrate, or we make it. We remove the solvent to concentrate the analyte. Right, this is efficient and wealth of available analytical data and widely accepted in many standard methods. It is and there's a large volume of purity solvents. Of course, for this method, we need to have a large volume, high purity solvents, right? And it is hazardous and yield small sample to solvent volume ratios. With a large volume of solvents, we only acquire a small volume of analyte. All right. To sample is also large, right? So meaning that we need to use a lot of a solvent for this. method. Wait for a while. And major to facilitate the automation and effective to reduce the consumption of organic solvent. To overcome this problem, the consumption of a really high volume of the organic solvent, we need an automated and effective method. All right. Solvent versus multiple smaller batch of solvent. All right. This is how to reduce the consumption of a large volume of solvent. So we do it in a separate step, right? For example, in the single extraction, we use 1 liter of water containing 10 grams of solute. All right, and then at the first stage, okay, the organic layer with 1 liter of the solvent, 1 liter of water. Okay, for example, we recovered 50%, right? Meaning that if we consider that our water sample is homogeneous with the analyte, with the solute, all right? So we get 5 grams of the analyte, and the balance of the analyte inside the sample is 5 grams, right? So for the liquid extraction shaken with organic solvent 1 liter and allowed to equilibrate, right? Since organic to aqueous ratio is now 1:1, the aqueous phase will now contain 5 grams of solute, while the organic layer will have 5 grams of solute. Right, so 5 grams is extracted. The recovery is 59%. Right. Using this method, right, 1 liter of water containing 10 grams of solute directly with 1 liter of organic and solvent. So we recovered only 50% of the analyte. Break up 1 liter organic solvent into 2 equal portions. For example, 500 ml for each. Okay, and then for 1 liter of water containing 10 grams of solute, and we shake it with 500 milliliter of organic solvent, right? And since organic to aqueous ratio is now 1:2, the aqueous now contains 6.666 grams of solute, while the organic layer will have 3.333 grams of solute. Right, so the LLE is shaken with organic solvent, 500 ml, and allowed to equilibrate. Repeat extraction for of aqueous layer containing 6.66 grams unextracted solute with another 500 ml of organic solvent. Then we have the total that been extracted is now 5.555 grams. So which one is better?
The first step.
The first step, right? Because now after we divide into 2 steps, okay, we divide the solvent into 2 steps. 55.55% of recovery. Recovery meaning that if we assume that we have 10 grams of solute, then after this step, we only extracted 5.555 grams of the solute. So the recovery is 55.55%, right? You see there? Okay. But the dual step is better than single extraction. Why? Can you explain that? Why the dual step is better than single extraction? Anybody can give your idea?
Can get accurate amount to extract the sample.
What?
Dual step is better than single because we can determine the accurate amount of samples to extract.
I'm sorry here. Okay. There's an error in the slide actually. Okay. All right. 5 gram from 10 gram is only 50%. So the first one is less than the second one. Notice that? You notice that?
Yes.
Okay, because some error here. Previously you seen 59, right? But the slide is, it is 50, not 59, right? So the second is better. When we divide the solvent, the process into a dual step, we divide the solvent 500 ml and 500 ml, right? Then we have better result, 55.55% of recovery. Okay. Can you understand this? Why? Right? Can you have the idea why?
Because we use 500 ml water. The aqueous.
We use 500 ml of the organic solvent, right?
Yes.
Since organic to aqueous ratio is now 1 to 2, the aqueous phase will now contain 6, because the ratio, you see the ratio, right? We have 1 liter of aqueous layer and 500 ml of organic solvent, right? So the ratio is now not 1 to 1, but 1 to 2. So the aqueous phase will now contain, because we assume this is at dynamic equilibrium, right? So the aqueous phase is now contain 6.666 gram, and the organic layer have 3.333 gram of solvent. It is based on the ratio. So when we do it in dual step, we have a better result. Okay. So meaning that the multiple batch will have a better result for the liquid extraction rather than a single batch. So if you break up 1 liter organic solvent into 4 equal portions, 500 and 250 ml for each. In example, we do 4 extraction 4 times instead of 1 time or 2 times, right? The first 250 ml we extract 2 gram, and then the second 250 ml we extract 1.6 gram, and then the third 250 ml we extract 1.28 grams, and the fourth 250 ml we extract 1.024 grams. So the recovery is now 59.04%. So multiple extraction using same volume of extractant produce better extraction recovery. But remember, we only break up the organic solvents into 4 volume, right? But the sample is remain at 1 liter, remember? Okay. For liquid extraction. So what type of solvent that we need to choose? There's a table that we need to refer. Characteristic of solvent commonly used in liquid extraction. We have non-polar to polar, right? We have from non-polar we have hexane, and the most polar we have acetic acid, right? We also can use the liquid extraction of metal ions using chelating agents, right? The chelating agent is the chemical or the compounds, right, in the form of solution, right, and also we have metal that we can dissolve, all right, that the molecules can trap a metals, right? See, we can see at the molecules we have a lot of, normally the chelating agent have a lot of lone pair, right? For example, this nitrogen, okay, in 8-hydroxyquinoline, right? We have lone pair here, right? Lone pair at the oxygen as well, right? We have lone pair here, right? And this type of compound can chelate metal, right? Can trap metal, not ionic bond, but in form of complex bonding, all right? So if you want to extract metals from the sample, we need to use reagent that have a chelating system, right? Normally a chemical that have the structure have a lot of lone pair electrons, right? Normally lone pairs from nitrogen and oxygen. See this, right? So how many lone pair for nitrogen normally? Like this bonding, how many lone pair for nitrogen? Okay. Refresh back your basic chemistry knowledge, right? It's a continued slide for the chelating agent, all right? Of pH on liquid extraction also can occur, okay? So we can adjust the pH to have a better extraction. Effect of pH on the extraction efficiency of selected metal ions using diathizone as chelatants. So now we go to the solid sample, right? We can either do solid liquid extraction or solid liquid extraction batch or continue. I would like to introduce to you the Soxhlet extraction. Okay, a Soxhlet extractor is a lab equipment of certain kinds of solids, and this device allows for continuous treatment of a sample with a solvent over a period of hours or days to extract compounds of interest. Typically, a Soxhlet extraction compound has a limited solubility in solvent, and if the impurity is insoluble in that solvent. Okay, now instead of liquid sample, now we have a solid sample. So now how to extract out the analyte, right, into the solvent from the solid sample. Okay, now we know that if our solid sample can easily dissolve in the solvent, so that's good. We just dissolve our solid sample in the solvent. But now the issue is we have a solid sample that is limited solubility, meaning that we have to force the sample, the solid sample, to dissolve in our solvent. So how to force it? Give me an example how to force our sample to dissolve in our solvent. Normally in chemistry, in chemical process, we need to put heat, right? And we need to extend the time, right? So we need to heat it longer time to ensure that all of the analyte will dissolve in our solvent, so that we can easily take the solvent for further action to pre-concentrate it, all right, and then to analyze using our chromatographic technique, right? And also we have to ensure that the impurities will not dissolve in the solvent, right? Extraction equipment, we have a stirrer bar, we have a steel pot, all right. The steel pot should not be overfilled, and the volume of solvent in the steel pot should be 3 to 4 times the volume of the Soxhlet chamber. We have the distillation path, we have a thimble, we have a solid, we have a siphon top, we have siphon exit, expansion adapter, condenser, cooling water in and cooling water out. So from this photo, from this diagram, can you imagine how the Soxhlet extractor looks like? Can you imagine that? See, in this equipment, in this apparatus, we need to heat here. We need to do a heating process. Okay, where we put our sample? Here, right? It will evaporate and will cool back. It will evaporate, condense down. Then the solvent will go inside the round bottom flask again. So we need to do it for a longer time to ensure that all the analyte will be dissolved in the solvent. Don't worry, I will show the video of the Soxhlet extraction. A solid material containing desired compound is placed inside a thimble and is loaded into the main chamber of the Soxhlet extractor. Right, so where to put the our sample is inside here. What is this thing? Is it the test tube? No. It is made by, this thing is made by normally a paper, all right, that can that do not react with the solvent and could be as the filter, right? For that only can allow the analytes to be extracted out in the solvent, right? So the sample, the solid sample with the impurities that or matrix that we don't want will remain in the thimble. We call it a thimble. The Soxhlet extractor is placed onto a flask containing the extraction solvent, right? The orange color solution is our solvent. All right. Okay, and then the solvent vapor travels up distillation arm and floods into the chamber, housing the thimble of solid. Okay, the solvent will evaporate and flood here in the around the thimble, okay, so that the solvent will extract out. Hopefully, the solvent will extract out all the analytes and back again into the round bottom flask, and the process is rotated, okay, again and again. When the Soxhlet chamber is almost full, the chamber is automatically emptied by a siphon arm. When it is full, right, up to here, it will automatically emptied back. All right. When the solvent running back down to the distillation task, this cycle may be allowed to repeat many times over hours or days. After many cycles, the desired compound is concentrated in the distillation flask by means of a rotary evaporator, yielding the extracted compound. The non-soluble portion of the extracted solid remains in the thimble and is usually discarded, right? Right, for example, we have 10 grams of flash plus 10 grams of anhydrous sodium sulfate plus 320 ml of acetohexane, 1-to-1 ratio. We for 16 hours, right, to filter it, and then we have a silica gel cleanup and we prepare a sample for the GC analysis. How the Soxhlet extractor looks like. Sorry. Do you have a class at 10?
No.
All right. I need to repeat it. I need to continue it for a while. Okay. For my students from Department of Chemistry that have joined this session, I have not done yet with my with the class with your first year, with your junior first year student of petroleum engineering. So let me finish it first. All right, so this is how the Soxhlet extractor looks like. Okay, it is messy, time consuming, and use a lot of organic solvent. Similar, okay, consume a lot of organic solvent and hazardous to health. Waste disposal problem and further concentration. So it is the most useful apparatus for solid liquid extraction in various fields such as pharmaceuticals. And nowadays, Soxhlet apparatus is still common and widely used as a referee and standard apparatus for the extraction of oil from various materials. So all these conventional methods that I have taught you has some problems. They use large amount of organic solvent, of course, methanol, ECM, and so on. And these solvents are hazardous to health and environment. And waste disposal problem, because we need to dispose the solvent that we have been used for this extraction, and pre-concentration step it in several days. But for liquid extraction, that we shake the separating funnel, okay, that require a lot of energy, all right, to shake it, all right. And then we have a long extraction time using Soxhlet, and then require large amount of sample also, right? Not only require large amount of solvent, but also large amount of sample. And some still carry contaminants. We produce interfering background in our analysis, right? That background that disturb our our analyte actual peaks in the chromatogram. So the solution is a trend has been to chemicals to minimize the environmental impact. And then we have also the solid phase extraction method, right? A solid phase extraction method consists of bringing a liquid or gaseous test sample in contact with a solid phase, right, whereby the analyte is selectively adsorbed on the surface of the solid phase, and other solvents such as liquids or gases added to remove possible adsorbed matrix components, and eluting solvent added to dissolve analyte selectively prior to instrumental analysis. Okay, now instead of using liquid extraction and Soxhlet, right, we also can use the solid phase extractor. We have a thing like syringe like this, right? Okay, it looks like syringe, right? So here we have a solid phase extractor inside, right? And then how we do is we just press the sample, for example, the solution sample inside this, and right, and we have a pre-filter, right, to filter out all the impurities first before we use the solid phase extract. Have we have a pre-filter here, we have a ring here, particle disc here, and support material, right? This is how it works. Okay, the SPE, the principles, right? We have to condition it first, right? Conditioning, and then loading sample. We put sample inside, right? For example, the red one is our light, and the interference are the the red circle is analyte. The interference are the green and the orange circle, right? So the idea is we filter out we just filter out the sample together with the analyte, and also we can separate the analyte and the interference using this type of SPE extractor, right? You can see here we just filter out the green rectangle, okay, this is the interference, and then we filter out the green triangle, which is also the interference, and then we can also filter the analyte. Okay, this is how it looks like. So the advantage of SPE is the extract, the organic phase can be injected directly to the instrument, and many established standard methods using this technique. The disadvantage presence of particulate matter in sample and can cause plugging of cartridge. When the particulate matter, right, the impurities in form of particulate matter inside our sample, we also require a lot of energy, right, to push it, right, to filter it, and also a large amount of organic. So we have a type of SPE phase, okay, packing material to choose, all right. A classic solvents, we have a polymer, we have polar and non-polar. Okay, we have to to ensure that we use a right type of SPE phase for our sample and analyte. So retention mechanism, hydrophobic, non-polar, and reverse phase. Okay, so typical phase CA, and in example PSDVB and strata X. And most sample and huge difference in polarity between phase and water. Organic compounds interact with organic solid phase due to their organic frame. Right, we have also the hydrophilic. Okay, see, we have ion SPE. We also need to choose the solvent using SPE. Right, it is polar or non-polar, strong reverse phase or weak reverse phase. Okay? And then is it miscible in water or not? This is sample characteristic for SPE procedure, right? Need to to ensure what type of sample first, what type of our analyte, right? Either it ionic or okay, or not ionic, okay, aqueous or organic. Okay, just refer to this table. What are the goals for the SPE, right? The first one is purification. You can see this before we use SPE, okay, we have a lot of interference peak, right? But after we use SPE, we have removed all the impurities so that we have less impurities background, the noise background in our chromatogram. Second one is for the concentration. Example from 1 liter to 1 ml of analyte, okay, of our sample that containing analyte. So we remove the matrix. And also for the third one is for solvent switch. For example, we want to switch the solvent ethanol. Okay, so 3 goals for solid phase extractor. And the applications, all right. For example, poor sample preparation, we have a yellow extract. Okay, after we use SPE, we have a colorless extract. Okay, original sample that before using SPE, and after we use SPE, we have a trace enrichment. Okay, we have also automated solid phase extraction system. Right, that's all for the sample preparation for the organic analytes. Now, you must watch 2 videos. The first one is the video on the liquid extraction using separating funnel, and the second one is a Soxhlet extractor. Okay, you need to watch the videos because you need to understand how the process is being done. Because using this slide, you're not able to imagine how it will be done for the 2 types of the liquid extraction and solid liquid extraction, right? The first one is a liquid extraction using separating funnel, and second video is on the solid liquid extraction using Soxhlet method, right? I will put the videos in the e-learning now. Okay, I have put one for the liquid section. I need to put one more for the Soxhlet. You need to watch, and then you need to ensure, you need to make sure you watch it today and confirm it in the WhatsApp group, right? Okay, do you have any question? That's all for today. Because for the solid phase extraction, you can imagine it just using a solid extractor inside a syringe, right? So you need to filter it. That is a concept. But for the Soxhlet and also the liquid extraction using separating funnel, you need to watch the video. Okay, you have any question?
No, Doctor.
Okay, so you are ready to watch the video? So you ready to watch the video?
I'm ready, Doctor.
Yes, good. So
Today we're going to look at a technique that
anybody want to scan the attendance? You have scanned the attendance, all of you?
Done.
Video, because liquid extraction is there, but Soxhlet extraction is not yet. Yes. All right, the video is now ready. So watch both the videos and then please in the WhatsApp group that you have done watching it. How about it? You understand about the video or not? Right? So just let me know. So thank you for today and see you next week in our last topic on this chromatography method. Okay, and then we have two other classic methods that I've got for the last chapter. We have last two chapters, which is gravimetric and volumetric methods, which is the classic methods. And you will there are no maybe there are no synchronized teaching like this. I will just upload the teaching video together with the slide that have been recorded. Okay, you need to watch it in the e-learning. Okay, and then we will have the last session on I think on Thursday maybe. Okay, to have some kind of conclusion of this course. We are at the end of the semester, guys. Do you notice that?
Yes.
Yes.
right? So maybe we have
Penuh dah habis.
so we we will have a revision after this. Okay. Do you want a revision before the final exam?
One
Together with me.
Uh,
Of course, right? So we will have a revision after the last. Okay. So on Sunday we will have a class on the calibration for the chromatography method, and then for volumetry and gravimetry analysis, okay, you will watch the video that I will upload in the e-learning, and then after that we will have a revision. Is it okay?
Okay.
All right, thank you for today. Remember to watch the video. Watch the
Thank you,
video.
Doctor.
Right. Okay, most welcome. Thank you. Assalamualaikum and bye-bye.
Waalaikumsalam.
Okay, watch the video.